All right, we have the applications of sine functions or sinusoidal functions for part 4 here. The two we did are the Ferris wheel here, and then down below is the number of hours of daylight. So let's get started. What I like to do with these problems, first thing you got to do, take a minute and read the entire paragraph or however long it is, read the entire setup. Make sure you understand, number one, what your background is, but number two, more importantly, make sure you understand what questions you need to answer. Because some of these can be a little lengthy, you got to make sure, read all the information, but then make sure you know where you're heading so that you know when you're done and what answers to circle. So first thing I would do is pause the video and read through the entire paragraph about the Ferris wheel. All right, then once you've read through and you fully understand from start to finish what you're doing, what you'll notice on this problem, it actually asks you to do this, but it says make a sketch showing the height above ground. Then it's kind of a two-part problem. Second thing you do is find a function. So in order to do that, I'm going to even do an additional step just so that we kind of have an idea what we're working with. Okay, but this is kind of our Ferris wheel. And you know what? I better make that a little bit lower. So this distance here is 10 feet. And then the radius here is 70 and 70. So that's just the basic sketch. They also tell us here about 3 rows up from the bottom. It says the Ferris wheel is spinning at 4 minutes per revolution. So that's all the information given. What we need to do is step 1, make a sketch with x-axis being time. So what that looks like is such, and that's 0, 0. This is time in minutes, and that's height in feet. There we go. What we know about this is that the person boards the gondola that is at the 6 o'clock position, so 6 o'clock down here means that the graph will start at 10 feet off the ground. If it takes 4 minutes to go all the way around, that means that to get to the very top, the peak, would be half of that time, assuming constant velocity, which we have to in this case. So halfway up, we would reach at 2 minutes. Because remember, the whole thing takes 4 minutes to go around, so it would take 2 minutes to get to the top. That top is, well, how far off the ground? It says height above ground. So starting at 10, at 2 minutes, they're at the peak, so like right here. And that peak is 10 plus 70 plus 70, or 150. Okay. Just kind of as a reference point, we'll put in here 80 feet. And in fact, I'll even draw a bit of a midline for reference. And then we know that later on here at the 4 minute mark, they should be back at 0. Sorry, 10. My fault. 10 feet off the ground because they're at the bottom of the Ferris wheel. So as they say, it's a sinusoidal graph. So we're going to go down there and up there. Perfect. All right. So I think we got everything. I may just mark that the midline where the graph turns negative to positive and positive negative, those happen to be equidistant parts would be 1 and then the halfway point, and 3 and then the end, because we're going constant velocity. So we'll just make those notes or later usage. So we have step 1 down, make a sketch showing the height. Find a function that models the height versus time. Okay, find the function. It doesn't say find a sine or cosine. It allows us to pick. So I'm going to go ahead and use sine for this. But first thing I want to do is identify some key characteristics. Amplitude. There we go. Perfect. Not actually perfect. So our amplitude is, again, that midline to the peak or midline to the valley. So from 80 to 150 or from 10 to 80. So we find that our amplitude is 70. I'll just fill in the rest, the period, the phase shift, and vertical shift. Doesn't matter the order we fill them in. Easiest one from here, not period or phase shift, but vertical shift, is that midline for a sine curve should be 0. Right? The graph uses a midline of the x-axis. So here our midline is at 80, so vertical shift is 80. Our phase shift, again, we've chosen sine curve, so that means that our graph should start on the y-axis 0, 0. We've accounted for the 80, but we've also shifted to the right by 1 minute, so our phase shift is 1. The period in this case, period is always 2 pi over b. In this case, that period is 4 minutes. So what we find is that it's actually 2 pi over 4 equals b, which the 2/4 reduces to 1/2, so pi over 2. The period, sorry, I should fill that in. The period is 4 minutes. So if we come back here and we say y is equal to a times sine, a is our amplitude, 70, sine b, so that's why I took the time to find b, because b is not just 4, right? Period and b are not the same. Pi over 2. Another set of parentheses, and then x minus c, so c is that phase shift. And then we close off the parentheses for both of those, and our vertical shift is up 80. All right, so real quick here, the final function's up there. I'm going to try and get in the second example, or well, the fifth one, but the second one of the applications here. So let's take a look. First thing you want to do, please make sure, take a second, pause the video, read the whole application, the whole story, make sure you understand what it is we're working with and what are the things we have to deliver by the end of this. So take a second, pause the video, we'll come back. Okay, so hopefully you've got all of it read through, you paused it, you found out that this one, notice that we don't actually have to sketch anything. We just have to write a sinusoidal equation. But what I'm going to say is, no matter whether it's required or not, it is so much more helpful to have a graph to reference your points based on your information off of. So let's do that. I'm going to create perfect axis. These are hours. Well, light, sorry. The unit is hours, but it's the amount of light in the day. Also, that starts at 0. And this is time in days. So if we look at this as one whole year, we'd have from 0 to 365, right? Because it is a non-leap year. The information we're given says the longest day is June 21st. I had 15.7 hours. So the longest day means I'm going to come up here to the top, arbitrarily pick that point, and say 15.7 hours. Now it also says later, note, June 21st is the 172nd day. So somewhere around, I mean, we all know that on the calendar here that it should be somewhere here, so 172nd of 365. So we can have this point here, right? We also know that the shortest day is December 21st. That has 8.3 hours. So let's call this 8.3, and that is somewhere around here on the 355th day. Squeeze that in, so that comes up to about right there. Now these are the only 2 points we're given. One thing I want to do is, again, we're going to find that midline. And for a couple reasons, you could do the math, add those two numbers, divide by 2. But the other thing is, if you didn't already know this, little background, you will always have 12 hours as the midline for your number of hours, whether you're in the North Pole, the South Pole, somewhere on the equator, or somewhere in between. You actually always have a midline of 12 hours of sunlight and 12 of daylight. Because again, your max is going to only ever be 24 or 0. So midline 12, I'm going to draw that in. And what we know is that it's sinusoidal. It says, write the sinusoidal equation. So we know that we have a peak here. We're going to come down and bottom out in December. But that's all we have. We don't even have a complete graph like example 4. Example 4 was a little more inclusive, but we can still make an equation. What I would say, though, it says write a sinusoidal function. Sinusoidal does only mean sine or cosine. It doesn't mean you have to write a sine function. And because the graph looks like, I see this more of a cosine because it starts at the peak. And we have exact points for that. So I'm going to use a cosine function. First thing we're going to do is identify those key points. Our amplitude is from 12 to 15.7 or down to 8.3. So that is an amplitude of 3.7. Our vertical shift, remember that midline should still be at 0, but it's up at 12. The period is how long does this process repeat, or like how long does it take? Well, hopefully you've figured this out, but the period of this equation is 365 because there's that many days in a year, and then as we repeat year to year, we get the same information or the same number of hours. Our phase shift is, well, cosine should start again on the y-axis over here. It should start at the peak, but we moved 172 days. Also, 2 pi over b is equal to our period 365. So b is just 2 pi over 365. And I would just leave it exactly like that. So our equation is y equal to 3.7 cosine of 2 pi over 365, parentheses, x minus our phase shift, plus our vertical shift. There you go. And that is example 5. So we're on to practice problems. I think we have a CFA coming up here in a couple of days, but that should get you everything you need.